Good evening, all the participants. It's my pleasure to introduce our esteemed resource person, Dr. Parvataneni Nagasrinivasu, a distinguished academician and researcher in the areas of artificial intelligence, biomedical imaging, and healthcare informatics. Dr. Srinivasu is currently associated with Amrita Vishwa Vidyapeetham, Amaravati, which is ranked among the top institutions in India. He is also a postdoctoral researcher at the Biomedical Data Analytics Research Group, Federal University of Ceará, Brazil, and a research fellow at INTI, International University, Malaysia. He has more than 13 years of teaching and research experience in higher education. His primary research interests include biomedical image analysis, artificial intelligence, deep learning, healthcare informatics, explainable AI, and smart diagnostic systems. Dr. Srinivasu has an outstanding research record with over 150 publications in reputed SCI, SCIE, Scoopers, and IEEE indexed journals and conferences. Notably, he has been recognized among the top 2% scientists globally by Stanford University for the years 2024 and 2025, a prestigious international recognition of research impact. He has also contributed significantly as a guest editor and associate editor for leading publishers such as Springer, Elsevier, Taylor and Francis, MDPI, and IZI Global, and serves as a reviewer for more than 50 high-impact international journals, including IEEE Transactions on Industrial Informatics and AI in Medicine. In addition, Dr. Srinivasu is the recipient of multiple international research grants, particularly from King Faisal University, Saudi Arabia, and holds several international patents in AI, IoT, and medical systems, granted and published in Australia and India. His work strongly bridges AI research and real-world healthcare applications, making his contributions highly relevant to today's FDP theme. We are indeed honored to have Dr. P. Srinivasu with us today for this session, and we look forward to gaining valuable insights from his expertise. Over to you, sir. Please commence the session.
Yeah, ma'am. Thank you for reading out the short bio, and I would like to specially thank the management of Srinidhi Institute of Science and Technology and the principal of the institute, as well as the program organizing committee, for giving me this opportunity to interact with you. So I will just share my PPT, and then please let me know if the screen is visible.
Yes, sir. It is visible.
Yeah, thank you, ma'am. So good evening, everyone. Thank you for connecting, and today I was fortunate to have an interaction with you, and towards the end of the session we can have some discussion the suitability of the models and the data dependencies and the other things that are really helpful for the real-time implementation in the healthcare domain. So today I'll be discussing on the impact of the XAI in the healthcare, and the use of the conventional classification models and the recent advancements like categorical boosting with multi-layer perceptron neural networks for classification of the breast cancer data. So basically, coming to the breast cancer data, we in some cases we need to work with the imaging data. So specifically like the CT scan images, and in some cases we'll be working with CSV files where we come across the structured data. So in either of the cases, we'll be dealing the data in a different way. In case if it is a structured data, especially like if it is tabular data, then we are going to use the conventional classification models. So hopefully the linear regression or logistic regression or gradient, something like multi-layer perceptrons or support vector missions or Naive-based classifiers, those things we could use. And if it is an image data, obviously we people will rely on the deep learning techniques like convolution neural network or DenseNet or ResNet or Inceptron V3 or GoogleNet, or even nowadays the people are using the YOLO as well. So frankly speaking, there is a tremendous transformation that has happened over the years. So earlier, when we started working with identification of the tumors or identification of the malignant tissues from the MRI images or from the CT scan images, we used to rely on the segmentation techniques. So like the K nearest neighborhood, or in some cases we used to use a genetic algorithm, or in some cases we used to use the fuzzy logic as well for like fuzzy C means, and those sort of things we used to use for segmenting the MRI images or the grayscale images, and we used to localize the tumor. And over the years, we started switching from the segmentation to the classification, where we people had started using the CNN, and they using the CNN. We people had started working with classification of the images, like whether there is a tumor or not. So earlier it is something like in the segmentation also we used to segment the images. We used to get a bitmap images of the tumor, and we people couldn't classify what class is it. But later on, from the classification, initially we had started working whether the MRI images having a tumor or not. And later on, we people had started migrating towards identifying the number of classes. So whether there are two classes, or if we are having three or four classes, what type of tumor is it? And now the things has changed, and now we are people working more towards the object detection. So like we no longer work with the conventional models like CNN or DenseNet or ResNet or VGG16, VGG19 or Inceptron V3, but we started working with the YOLO model or efficient det, these sort of object detection models we had started using. So like there are a lot of transformations that has happened, and every time there is a change in the data as well. So earlier the data is not too complex. The size of the images are too small. It is something like in some cases it is 128 by 128. In few cases it is 256 by 256, and in few cases we used to work with 512 by 512. So, but over the years, there is a change in the equipment. There are a lot of sophisticated things has came in, and now there are a few cases where we work with 1024 by 1024 images or beyond that. So when the data is very complex, obviously we people have to rely on the complex models for understanding the patterns in the data, or underlying or understanding the underlying insights from the data. So maybe in today's session, I'll just go through a few things like what is the impact of XAI, like what XAI models we are going to use, and then we'll be discussing about like these are the topics I thought of. I'm sorry. These are the topics I thought of discussing, the role of XAI, and then we'll be discussing about the model selection depending upon the data that we are considering. And then the impact of the hyperparameters, because the hyperparameters plays a crucial role. It could be a conventional classification model or a machine learning model like SVM or something like a multi-layer perceptron or J48 or linear regression or logistic regression or anything. So there also we do have the hyperparameters like what would be the learning rate and how many epos and all those things. Even in the recent advancement like the deep learning or else in the object detection models like YOLO, we still have the hyperparameters which usually helps us in understanding how well the model is able to generalize the data, like how it is performing on the training data, how it is performing on the testing data, or how do we need to further extend the validation or fine tuning of the model. Those things we will be able to understand. And after that, like, so what are the different metrics that we could consider in optimizing the models? And finally, the role of categorical boosting to work with multi-layer perceptron. So, of course, either of them are not new things, like the categorical boosting or the multi-layer perceptrons are not very recent advancements, but still then when we try to integrate either of them, so there is a very high possibility that we'll be getting the models with a better accuracy. So what I mean to say is like for classifying the data, let us assume if it is a tabular data, if it is a CSV file, for classifying the data from a CSV file, frankly speaking, we don't really need a very recent advanced model like CNN or something else for classifying the data. What I mean to say is like when we are using a very complex data, that obviously we people have to rely on a complex model, and when we rely on a complex model, so we people also have to think about what is the computational requirement and what are the other things like the technical feasibility and the economical feasibility comes into the picture when we start using a complex model. See, we all know that so the quantum computing yields us a better outcome than the conventional models. But at the same point of time, not in all the cases the quantum computing would yield say like it yields a better result. I'm sorry, but the thing is like not in all the cases it is computationally efficient. So basically, hardly. We people have to pay a lot for using the quantum computer for minutes, and hardly we need a fraction of minutes or maybe fraction of seconds as well in some cases for calculating the for computing the model or for applying the model and get the results. So if that is the case, is it really required for us to migrate from a conventional model which is giving us around 97-98% of accuracy to a very recent advancement model from 97 to 98% accuracy? I'm not criticizing the quantum computing or I'm not criticizing something else, but the question here is like, if a conventional model could give us a decent performance with a 98 or 97 percentage of accuracy, is it really required to change the model over there? Do we need to really use a quantum computing in that particular context? So if the problem is really complex and if we are working with a larger size data set and if it is too complex, or let it be, if we are working with a high dimensional data like genomic data, it is vast data, and the conventional systems or maybe the GPUs or TPUs are not really adequate or they are not really sufficient enough to deal with such a large volume of data. Then obviously we people have to rely on quantum computing for better performance and for better experience of getting the results. But for a simple models like working with a CSV file having some 10,000 records and having some 15 different features or 30 different features, we really don't need to work with quantum computing. So those things we can just discuss over here, like what is the significance of having, or what is the significance of using categorical boosting and with the conventional multi-layer perceptron model for classifying the data. So the first thing is like the role of XAI here. So usually the people used to think that the XAI is going to increase the performance of the model. So like they are in misinterpretation, like if we are going to use XAI, so if the accuracy is like 20 percentage or sorry, accuracy is like 90 percentage or 85 percentage, the people usually used to think like we'll be getting a model which is whose accuracy would be somewhere close to 99 or 98. But frankly speaking, the XAI doesn't have any significant, not significant, it doesn't have any impact on the performance of the model. So what I mean to say is like these XAI tools are just meant for the interpretability of the model. So sometimes we people might be worried like how the model is giving a 98% accuracy or 99% accuracy. Is the model biased? Biased in the sense, in some cases, usually nowadays we come across a problem like there is a data leakage that happening when we are training the model. So when the data leakage happens, then obviously the model is going to show us, or we are able to obtain a 98 or 99% of accuracy. Frankly speaking, the model will not be able to yield that much of accuracy if the data leakage doesn't occur. So now basically, in order to validate or in order to understand the black box models, So it is one of an assistive tool which could help us out to understand on what basis the model, the machine learning model or a deep learning model is able to come to that particular conclusion. So if it says like the given record is having a tumor, or else if it is a malignant, or if it is something like if we are checking for a diabetes, as that maybe we give a PIMA data set or something. If it gives an output like that particular record is associated with a diabetic patient, or if a particular record is not associated with a diabetic patient, if the machine learning model is classifying that. So these XAI models are going to assist us. So what are all the features does the model consider? So that it came to a conclusion that that particular record is associated with a tumorous region, or that particular record is associated with a diabetic patient. So basically, the model is going to yield us 98 or 97 or 99% accuracy. At some point of time, we might get a doubt. Is it really true that the model is giving us that much of good accuracy? Because in some cases, even the human is going to fail, but the machines doesn't fail. Like they're in few instances, not in all the instances, they are giving the better accuracy than the humans. So we might be getting a doubt, like, is it really true that we are getting 97 or 98% accuracy? Then in order to analyze, so how the model is going to process the data and how the model came to that conclusion. So we are going to use these XAI models. But however, these XAI models really don't give any impact on, or they doesn't have any impact on the performance of the model. So what actually they do is like, I'll just give you an example. We are having two models that are widely used. So one is Lime and the other one is Sharp. So these are used for the local explainability. There are two different types of explainabilities. One is the local explainability and the other one is a global explainability. So basically, these two models, the Lime and Sharp, are the two models which are extensively used for performing the local explainability. So now, what actually the local explainability is all about means, so let us assume if we are taking a diabetic data set and we are supposed to classify whether that particular record is associated with a diabetic patient or not. So now basically in order to determine the things, so we usually take the body mass into consideration, or else his age into consideration, or else his skin thickness into consideration. Like there are few things we usually take the body, the insulin content into consideration. So these are the factors that are given a considerable weightage in order to determine whether that particular record is associated with the diabetic or not. But there is nothing to do with the name of the person, or the demographic location of the person, his mobile number or his email ID or his father's name. They really doesn't contribute in determining whether that record is associated with a diabetic patient or not. So that is one example. And basically these XAI models like the Lime and Sharp, what they do is like, they're going to tell, so what are all the features that are really significant in making the decision, and what is the relationship between either of those features. So like in the data set, if we are having 15 columns and those 15 of them are the features. Now, basically out of 15, maybe four features or three features or five features are significant. And basically these Sharp and Lime are going to assist us in identifying those highly significant features. That is one thing that they are going to do. And the other thing is like they're going to assist us in analyzing the relation between them. So whether they are closely related or they are sparsely related, or what type of dependency do they have. So those are for analyzing that, these XAI models are being used. So in our current study also, we people had discussed something like we are using XAI. So if you go back to the title and if you're going to see, there is a discussion about the XAI. So in this particular context, the XAI is going to give us the local explainability of the model. So what are all the features that are being considered, and what is the significance of those features, and what is the dependency among them. So those sort of things that these either of these local models are going to give. But however, they really don't have any impact on the performance. And moreover, these are going to assist us in better debugging the model. So sometimes if the model is not performing well, so if we, in case if we are going to use the XAI models, so it could easily show us what are all the features that are being considered. So like I could give you one other example. Like if there is a student, and if we really want to check, or if we want to classify the student record, whether he will be going to a service-based company or a product-based company. So now, basically, there are multiple things. Maybe we are going to take the student's GPA into consideration, or the student's number of certifications into consideration, or else the student's number of backlogs into consideration. So, like, there are some parameters we really consider. Now, if the model is also considering the same parameters to determine whether the student will be placed in a service-based company or a product-based company, then that's well and good. If at all, if the model misinterprets, and if it takes some other lesser significant features like the age of a student, where it doesn't have anything to do with the service-based company or product-based company, or else the demographic location of the student, there is nothing to do to decide whether he will be placed in a service-based company or a product-based company, or else his mobile number, there is nothing to do to determine whether he will be placed in a service-based company or a product-based company. So basically, when we apply these XAI models, so if the model is also picking the higher significant features, and if it is able to recognize that correctly, then that is fair enough. If at all, if it is taking a wrong feature, like the age into consideration, rather than taking the number of backlogs into consideration, now what actually happens is like, but still, if it is giving a better accuracy means, so despite of taking a wrong features, if it is still giving a better accuracy means, some way the model is being biased, in the sense like it is biased towards a particular class. Or else, in some cases, it also assists us in debugging the model. Debugging in the sense like, if the model doesn't gives us accuracy beyond 80% or 85%. So in order to troubleshoot where exactly the problem lies, so if it is with the features, or if it is something else with the other aspects like calculating the weights, or if it is with the regularizer, or if it is with the activation function or something else, in order to localize the problem, we still use the explainable AI models so that we can just see what are all the features that it is considering. If at all, if it is considering the wrong features, then we could easily say the feature engineering model goes wrong. So in that manner, this XAI is going to help us out to have a better comprehensibility on the way how the machine learning model is going to work. Nowadays, even the deep learning models are also using XAI. So where if you could see, it is going to generate a heat map. So like what all the features in the image are being considered for making a decision. So that is the role, and that is the impact of XAI. And after that, coming to the model selection, so we do have different types of data that are available. And in some cases, we are going to work with the tabular data or well-structured data. So when it is a well-structured data, we obviously have something like the CSV files, as it is mentioned over here. Or else sometimes we are going to work with the databases, or else sometimes we are going to work with the sensor reading. So like the temperature we are going to read, and then we are going to record that, and we are going to make some sort of forecasting based on that. Or else in some cases we are going to have the EHRs. We usually call them as a clinical records, electronic healthcare records. So like we are going to make the record of everything, how frequently they are going to they are visiting the hospital, and for what purpose they are visiting the hospital, and what is his body mass index, what is his height, or what is his age, and all those things. And based on the data, we could make a prediction. And even the insurance companies are nowadays using that electronic healthcare records to decide what would be his insurance premium. So like even the companies, they have started using this data for analyzing uh, analyzing like the healthcare related matters, like whether they could be given insurance or not, where what is a possibility that he would be having a cardiac disease after 20 years. So those sort of forecastings they are making based on this structured and the tabular data. And when we work with the CSV files, we obviously need not rely on a high complex models. We could still rely on the conventional classification techniques like the random forest, or gradient boosting, or the decision trees, or the the linear regression or the logistic regression, those sort of things we could use. So we really need not switch to a more complex things, but basically they could only work with the smaller size data sets. If the data set is very complex, then obviously we people have to switch on to a complex model. But when the data set is size is very small, then we can still work with the conventional classification models. And they are capable of dealing with the data, which is in a combination of numerical and categorical data as well. So categorical data in the sense like if we are going to have multiple classes and if we are going to label them like that, or else if we are going to say a group of samples as class A and a group of samples as class B and a group of samples as class C, then we still consider that as a categorical data. So that is in that particular context, we could still use these conventional models, and then or else the models that needs the interpretability. So like sometimes when a particular conclusion was made, if we people really want to know on what basis the conclusion was made, so even in that particular case, it is still good to work with these conventional classification models, because they are comparatively lesser complex than the advanced models, and they are easily understandable, or they are easily comprehensible to know how the actual process happens there. And the other thing is like the text data. So usually the unstructured data, sometimes we are going to get the customer feedbacks, or in some cases we are going to get the Twitter data in order to analyze the data, or sometimes for the sentiment analysis or for summarizing the contents. So if that those things, they all generally falls under the unstructured data. And if that is the case, we usually get the data from the documents, or in some cases we are going to get the data from the reviews, or sometimes even in software engineering, the requirements could also be written as a piece of text, which needs in detailed analysis of that for better understanding of the customer requirement, and even the data from the emails. So they generally falls under the unstructured data. So when we are working with the unstructured data, so we obviously make use of the GPT or BERT, or the other advanced things, or word to vector, or something like the TF-IDF or the other thing. So like term frequency and inverse document frequency, or the other things that we are going to use. So when we are working with the unstructured data, the Navi-based classifier could also be used. So these are the very common techniques that we use when we are working with the unstructured data. Basically, that unstructured data is meant for something like for getting the required data for the recommender system. So based on the customer reviews, they are going to summarize the sentiment on the particular product, or they could collect the feedback on a particular item, or else they could also make a sentiment analysis. So in that particular context, they are going to work with the text-based data, which is usually unstructured data. And apart from this one, this is the other data that we largely work with. So like the image data. So the majority of the cases we come across the medical data, basically the CT scan images, or the MRI images, or the PET scan images. So or the X-ray, even the X-ray images or panoramic X-ray images, they all generally falls under the multimodal medical imaging. And the other thing is like the satellite data. Sometimes when we are capturing the images of the agricultural fields, or in order to assess the extent of a particular crop, or else even the sensor data, like in order to analyze the rare earth materials or something. So where we are going to work with the satellite images. And the other one is like the real-time images. Basically, they are meant for identifying the context from the image, or sometimes they are being used for the facial recognition. So when we are working with the image data, obviously we people start working with the complex data, like or the complex models, like convolutional neural networks, or ResNet, or VGG, or EfficientNet, or the other things like DenseNet, GoogleNet, MobileNet. So there are many such things. So these are the models we are going to use, and vision transformers or swing transformers. So these are the other common things that we usually use when we are working with the imaging data. And these models are very complex, and obviously we people need the GPUs or TPUs for processing the data. And basically, these are used when the data size is larger. And obviously, for training a supervised model, all these generally falls, not generally, these all are the supervised techniques. So when it comes to a supervised technique, obviously we people need to train the model. And in order to train the model, we obviously need the labeled data set. So when the data set is labeled, and when usually we work with the larger size data sets, so we obviously prefer to work on these things. And basically, each of them are going to have some sort of spatial patterns, or we usually call it as underlying insights in the data, or the visual features that are used for classifying the data. So like giving an image of MRI and asking whether there is a tumor or not, or what type of tumor is it, or else what is the impact of the tumor. So even nowadays, we are using some models like UNet and other things like even for generating the images, we are going to use GAN, and all these things would also be used along with these models that I had mentioned over here when we are working with the image data. And the other one is the temporal data, so which is a time dependent data. And basically, when we are working with the time dependent data, so we usually make predictions about what is going to happen, like what would be the price of a particular share after 5 years, or what could be the price of a gold after a couple of weeks, or what could be the price of silver tomorrow. So, or what could be the temperature down the line after 10 years? If those sort of predictions we are going to make, then we obviously rely on the time series data, which is continuous in nature. And when we are working with that, obviously there is some sort of dependencies that are associated with a long-term data. So like when we want to predict what would be the price of gold after 5 years, we people must be analyzing what is the price of gold today, what is the price of gold 3 years back, what is the price of gold 5 years back, and what is the price of gold 7 years back, and what is the price of gold 10 years back. So we take all the data, we take the inflation into consideration, and we take the other important factors, and then we are going to make an assessment. This could be a possible price of gold after 5 years, or maybe this could be the possible cost of gold after 10 years. So basically, if that is a case, we obviously need to rely on some techniques like long short-term memory, which is capable of retaining the historical information. So even the RNNs could also be used. Recurrent neural networks could also be used. Basically, this LSTM and GRU, gated recurrent unit, or type of recurrent neural networks. Other one is like ARIMA and SARIMA are the other things that could also be used. And the other one is like the temporal convolution neural network. So depends upon the data. If it is a ECG data or EEG data, basically this data is used in medical domain. And the other things are like the activity log and stock prices are like for the business purpose, and the activity logs are used in the network security domain as well, or for analyzing the network performances and all. So whenever we work with those sort of data, then obviously we people have to work with these models. And again, these models like LSTM or GRU couldn't be used alone. So again, we need a baseline model, and along with the baseline model, we are going to use the LSTM or GRU. So that is the reason why very often we come across CNN with LSTM, or DenseNet with LSTM, or ResNet with LSTM, or MobileNet with LSTM. So even LSTM by LSTM, like that, we people usually use. And after this, I'm sorry, coming to the graph and network data. So basically, this type of data we usually see in the networking, like when we want to analyze the performance of a network, or else when we want to see how the nodes are connected in the social networks, or else what is the dependency among them, or what is the key node in the network, or those sort of things. Obviously, we usually get the network data, and basically they are meant for analyzing the dependencies of the relationship between the entities in the network. So basically, or else in order to make some sort of predictions. So maybe when we are working with the wireless sensor network, so we are going to have multiple nodes, and we people are going to analyze that to determine what would be the cluster head, and how we people could divide the nodes into clusters, and which node would be responsible for communicating with the sink, or those sort of things we usually do. And there we are going to work with graph-based neural network. And no, this is not really very advanced one, but we still work with that. And then the graph-based convolution neural network, and something like graph sage, and these sort of approaches we usually use. But this particular data is more about the social media data, or the networking data, which is used for identifying the entities, or their relations and all. So there we are going to use these models. And coming and even here you could get it out, like where we are going to use this network data. So there is something called as an technology called ambient assisted living. So let us assume in a particular community where there is a community that is remotely available, or where there is a community where the community is having the elderly people. And obviously, these elderly people need some sort of assistance when they are staying alone. And what they usually do is, like, whenever there are some techniques which are like in the ambient assistive technology, or in ambient assistive living technology, they are going to deploy the sensors. Whenever a senior citizen fell down, or if there is an abnormal activity, or else they are going to have a sensors even on the body. And when the blood glucose sensor senses that the blood glucose level is below the threshold, then they're going to alarm the caretaker nearby. So in some cases, what actually happens is, like uh, sometimes if there is a lesser blood glucose level for a diabetic patient, so if it goes below the minimum threshold, if it is something like the blood glucose level goes below 50 or something, then obviously the person is going to faint. When the person faints, obviously they are going to notify the caretaker, and they're going to notify the nearest primary healthcare center that there is some sort of abnormality has observed, and please immediately rush to the particular individual. So if that is the case, then obviously they are going to come to the patient. And in some cases, if there is a cardiac arrest, or there is something like some abnormality like a cardiac stroke or brain stroke has occurred, so now what they immediately do is, like, they have to notify the corresponding hospital, and then they have to make sure that proper care and immediate action is needed. Now, basically, what they do is, like, they're going to maintain a network of hospitals. So, in case if a physician is not available in the parent hospital, they switch on to the some other network hospital where they could provide the necessary assistance. So, like in that is one of the scenario where they need to work with network-based data, and even notifying the caretakers if there are multiple caretakers available in that particular region. Who is the caretaker who is readily available and who is closely available to that particular individual, like what is the vicinity, whether he is available within kilometer or within couple of kilometers. So they are going to use this graph based data or graph-based networks. And the other one is like high dimensional or the sparse data. So it is like the genomic data, which is of having too many records, and each of record is of uh, a very lengthy record. Or some cases like working with the recommender system, or the data that is having higher dimensions. Like if there are 1 lakh records, and if there are 500 columns, in the sense like 500 features, each column represents a one feature. If there are 500 features, basically it is quite challenging for a conventional classification model like a support vector machine or random forest or a decision tree or even for a multi-layer perceptron to scale them down to 10 features or 15 features out of 500. Every time they have to do the feature engineering where the features are being selected, and feature weights are being decided, and feature ranking is done, and all those things that obviously needs a lot of efforts. Then basically, if that is the case, basically they are going to use a lasso or lasso regression or principal component analysis, or even the auto encoders will also be used there for performing the feature engineering. So like when we are working with this high dimensional data, obviously we people will work with lasso regression or something else like the principal component analysis or LDA or something like the autoencoders. Especially when we are working with the imaging data, we prefer to work with autoencoders. So that's the way how these are the different models that we are going to use with the different types of data. And that is all about what model we people need to select based on the data that we are having. And followed by coming to the hyperparameters. So if we could see this diagram itself is going to say what is the significance of working with the hyperparameters. So usually we all are aware when we are writing the research articles or when we are working on any specific projects or when we are working with any given model, we usually prefer to perform the data pre-processing. So like filling out the missing data, or else in some cases, we are going to do the scaling of the data, like fixing the range of the data values. Or in some cases, we are going to do the data normalization, or sometimes we are going to do the batch processing, or sometimes we are going to do the data balancing, like Smart or something we are going to use for the data balancing, or we are going to apply different type of data augmentations, and that would obviously have a significant impact on the performance. So without performing this pre-processing, so if the model is getting a 90 percentage of accuracy on performing or on applying these pre-processing techniques like scaling or normalization of the data balancing or data augmentation or something, then obviously it is going to have the significant impact on the performance. Like the performance might jump all the way from 90 percentage to 96 percentage or 97 percentage on performing these things. Even that's also applicable for the imaging data as well. So where we are going to perform the contrast enhancement, we are going to perform the rotation, we are going to perform the flipping, we are going to perform the shear operation, or there are different operations that we do perform on the imaging data as well. So that would definitely have an impact on the performance of the system. In majority of the cases, basically these data augmentations will have a positive impact, but there are few cases where the model might diverge as well. But in majority of the cases, they are going to work perfectly fine. So diverging in the sense, basically, let us assume when there is some noise in the data. So like if it is a speckle noise, or if it is a salt and pepper noise, or Gaussian noise, or some, let us assume if there is some noise in the data. So what we usually do is like, we try to denoise the images before we give it as an input for the deep learning model. But it is not a mandatory thing to pre-process. But what we do is like, we thought like if we could reduce the noise, the model might be able to give a better performance. And if we are going to do that, obviously it is going to smoothen the image. So because when there is some noise, so let us assume if we are going to consider this as a image patch size, the kernel sizes of 3 by 3. Now there are 3 pixels over here, sorry, 9 pixels over here. So 3 rows and 3 columns. Now let us assume if there is some error or if there is some noise in the middle pixel, then what we do is like, we are going to calculate the mean, or we are going to calculate the average of all these pixels, and then all the surrounded pixels or all the neighboring pixels, and then we are going to decide what could be the value of that particular pixel. Now what happens is like, that particular region would be smoothened, in a sense that particular region might miss out the crucial information. When we miss out the crucial information, and when we fed these images as an input for our deep learning model, there is no guarantee that the deep learning model is going to learn from the images. Like in some cases, we might also end up with a misinterpretation, or it learns the wrong features, and then it completely end up with poor accuracy. So like, it is going to have both the positive impact and the negative impact, but in majority of the cases, this data augmentation or data pre-processing will be having a significant performance. But here, when when the hyperparameters are not appropriately calibrated, then obviously it is going to have a very serious impact on the performance of the model. So what I mean to say is even after we perform all these things, after performing the scaling, normalization, or data balancing, or the data augmentation, if we people ignore the hyperparameters, if we are least bothered about the hyperparameters, sometimes what we do is especially for the undergraduation projects, when the students comes to us, so what we usually say is it is something if the students are executing the model with 30 appos, or let it be, if they're running it with 50 appos, and if the accuracy is 92 or 93 percentage, the moment we realize that the accuracy is 92 or 93, we feel like it is of lesser accuracy. And then we are going to ask the students to make that 50 appos as 100 appos. Now, what happens is it takes a lot of time for executing the model. That is one impact. And the other thing is when we are going to significantly increase the number of appos, it obviously leads to a overfitting, because the model will be overtrained. And when the model is overtrained, it performs well on the training data, but it doesn't perform well on the unseen data. Then what happens is the model will be overfitted. And if the model was overfitted, we don't really say that the model is fine-tuned. So that's what the impact of the hyperparameters, and they are going to have a complete control on the learning process. So for at what pace the model has to learn, and until what time, or when the training has to be, when the learning process has to be stopped, all those things would be determined by the hyperparameters. So that is the reason why now even the hyperparameters are equally weighted like the pre-processing techniques. Even if we perform these and if we ignore these, the model is going to fail. Or else, even if we perform this and if we completely ignore this, in that case also the model is going to fail. So we people have to go hand in hand, and we people have to balance both the hyperparameters and as well as the pre-processing of the data. So why I was discussing this hyperparameters means the categorical boosting is one of the pre-processing technique that we are going to apply on the data, so that the multi-layer perceptron model is going to yield a better performance. So that is the reason why we are discussing about this. And basically, when we have started working with the models, we also have a discussion about the hyperparameters as well, which is very crucial in determining what would be the impact of the model, or what would be the impact of the system on the data, or in generalizing the data. So we usually come across two things. One is the underfitting and the other one is overfitting. So underfitting is something when we doesn't have adequate size data, or when we doesn't have adequate data to train the model, then we usually come across underfitting. Or else if we allow the model to learn from a fewer patterns, or with a lesser amount of data, or if the number of appos are very less, then obviously the model couldn't learn adequately from the data. It really doesn't capture the underlying patterns from the data, and then resultantly what is going to happen is it would fail on both the testing samples as well as on the training samples. In either of the cases, the model is going to fail, because it really couldn't understand the underlying patterns, or what are the features that are significant. Even it couldn't learn the features as well. So then we usually call that as underfitting. So it is something I can give an example. When the COVID-19 has started, just then the X-ray images has came to the market for the research, but those X-ray images are very divergent. So because there are different X-raying equipment being used, and basically the image modalities were different. Some equipment gives an X-ray image of size 512 by 512, and some gives an 1024 by 1024, like that. So when they started working, the initial challenge that they had faced is the inadequacy of the data. When the data was inadequate, then when we try to implement the model, obviously the model is going to fail, because it doesn't have adequate data to train the model. Then that is one of the impact. And the other thing is the overfitting. So where we rigorously train the model with plenty of or large volumes of data, and resultant what is going to happen is the model will also learn from the noise as well as from the outliers. And when it is learning from the noise, or when it learns the noise, then obviously what happens is like it will start diverging. It performs well on the training data, but it performs poorly on the validation data or on the testing data. In the sense, it couldn't generalize the unseen data in case of the overfitting. So like either of these cases are going to seriously impact the performance of the model. So underfitting, where the model couldn't learn appropriately or adequately from the data, so which is going to have a significant impact on the performance of the model, where the model couldn't perform well both on training data and the testing data. And whereas the overfitting is a scenario where the model is excessively trained, where it start where once after it start learning from the required features, then it will start learning the noise and the other things, like the even it also take the outliers into consideration, and then it is going to have a significant impact on the performance of the model. It is going to work perfectly fine on the training data, but when it is being evaluated on unseen data or on the testing data, then obviously the model is going to fail. Now, what is that, on how we are going to determine whether the model is overfitted or underfitted means? Basically, we are having the other things like, I'm sorry, here, these are the different hyperparameters we usually have. So one is like the batch size, what would be the size of the batch, and the number of epochs, as I had told to you, when it is having a fewer number of epochs or when it is having a larger number of epochs, then obviously it would be challenging for the model as well. So like pure epochs means maybe the model couldn't learn properly, and if there are more number of epochs means there is a possibility that the model might overlearn, or it leads to overfitting. And the learning rate, which is going to determine at what pace the model has to learn. And then the optimizer. So what could be the optimizer that could be used with the model? And then the activation function. So very often we come across a ReLU, and ReLU is a one type of activation function that we usually use. And the other one is a dropout factor and the regularization. So which are something like regularization is going to penalize the features, and dropout factor is going to, or dropout is going to decide what percentage of the features that are being selected could be dropped. So like if the dropout factor is 0.2, or if the dropout factor is 0.3, so it means that 30% of the features that are, or the trainable parameters are being dropped. Not if it is dropout factor is 0.2, so it is something like the 20% of lesser significant features could be dropped from the further evaluation. So when some of the features are dropped, or when the model is being penalized, then obviously there is less possibility of overfitting. Basically, these are the things that are going to assist us to come out of the overfitting scenario. So let us go in detail with each of them. So, and after that, we people can learn about what are the parameters that we consider in order to determine whether the model is overfitting or underfitting. So the first thing is like, anyway, this is the impact of the hyperparameters I had already told to you. So basically, they are meant for deciding at what pace the model must be learning. So whether it has to go for a faster convergence, and or else it has to go in slower convergence. So when basically the hyperparameters are going to decide. So it maybe the learning pace could be decided based on the learning rate. So if the learning rate is 0.01, so the model is going to learn faster. And basically, in some cases, if the learning rate is 0.0001, so the model is going to learn very slow. So either of them are going to have its own problem. So here, what happens is like when the learning rate is very slow, then there is a possibility like the model might end up in local maxima or local minima. There is other problem. And the other case is like when the learning rate is high. So sometimes the model will diverge from the optimal point. So, or the local, it is going to move away from the local best solution. So even that is the case, the model is going to fail. So depends upon the data, and we people are going to test the system with the different learning rates. So we are going to do the statistical analysis. What is the performance of the model when the learning rate is 0.01? What is the performance of the model when the learning rate is 0.001? and what is the performance of the model when the learning rate is 0.0001. And likewise, we are going to test the model at some point where the model is going to give us a better accuracy, then we are going to confine ourselves like this is the optimal learning rate for this given data. So we can't just seeing the data, or by seeing the model we couldn't decide what would be the optimal learning rate. And learning rate is going to decide the pace of learning, whether the learning process must go slower or the learning process must go faster. But either of them are going to have its own challenges. It is something like, excuse me, I'm having a call. Excuse me. I'm sorry, am I audible? Someone, could you please confirm? Yeah, there was a message. Okay.
Sir, audible, sir.
Yeah. Sorry. Yeah, thank you. Thank you. I got a call and I couldn't avoid that, so I just go out and come back. So fine. Getting back to the discussion, that is what the significance of hyperparameters, and like going through the impact of each of them. So the first one is the batch size. So basically, in the neural networks, what actually happens is like when there are two things, like from input. Let us assume if this has an input, and there are multiple layers like this, and then there would be an output. So basically the model is going to move from the input to the output. And basically what actually happens is like at each layer, there are a set of neurons that are being used. So there are a set of neurons here, 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 and there are a set of neurons here. So now, in order to determine which among those neurons are very significant, so we are going to assign the weights. So if at all, if a particular feature is important, or if a particular neuron is important, so we are going to give a more weight. And if a particular feature or a particular neuron is lesser significant, we are going to reduce the weight. Now, what actually happens is like in the forward direction, we are going to update the weights, and in the reverse direction, we are going to correct the weights. So like this is a forward pass and this is a backward pass. So now basically the batch size, of course, there is a lot of other explanation regarding this, but I just want to confine because we don't have much time out here. So in the batch size, what actually we do is like, if the batch size is larger, so it is going to converge faster. But at the same point of time, basically, we are able to calculate a more stable gradient. That is the other advantage when the batch size is larger. But at the same point of time, it might lead to overfitting. So basically, what does a batch size means? How many number of samples that we pass to the model, or from how we are going to send the model to learn before the weights are being updated. So that is what the batch size. So sometimes the batch size is 32, or sometimes the batch size is 64. In the sense, if it is 32 means, basically we are going to send 32 samples to the model to learn well before the weights are being updated. So basically that is what the impact of the batch size. So if the batch size is larger, it is going to assist us in better convergence or faster convergence, and able to calculate a better stable gradient. But at the same time, there is a very high possibility of overfitting. And if at all, if the batch size is smaller, then obviously it takes a more amount of time for convergence. And there is a possibility like it is going to learn from the noise as well. So that is a main challenge about the deciding the batch size. And the other one is like the number of epochs. So number of epochs is like for how many rounds or for how many iterations we are going to train the model. So let us assume if there are 1,000 images or 1,000 samples in the data set, and out of which 70% of them are used for training, and 10% of them are used for the validation, and 20% of them are used for the testing. So training and validation is something like one in the validation, And testing is like completely giving unseen data, and then we are going to test how well the model is going to work. And the validation partition or the validation samples are those that are meant for fine tuning the model. So based on the validation outcome, they are going to adjust the model hyperparameters. So now, basically, when the appos, or like if we mention it as a 50 appos, so for 50 times, we are going to send those 700 training samples for training the model. All the 700 samples, we are going to send it for 50 times for training the model. So that the appos could be lesser, or if appos could be more, as I had told to you earlier. So if we feel like the 50 appos are not giving us a better accuracy, and if we make it as 100 or 150 or 200 appos, it doesn't mean that the model is going to give us a better accuracy. But the thing is, like, if it is if the model is having a lesser number of appos, then it couldn't learn the underlying patterns from the data. And if it couldn't learn the underlying patterns from the data adequately, then obviously it is going to have a lesser performance, or a lesser generalization performance, which we usually call it as a underfitting. So, and when there are more number of appos, then obviously we are going to rigorously train the model. And in some cases, what happens is, like, if the model was trained beyond the limit, then it will start learning from the noisy data, as I had discussed with you in the previous slide. Then when it starts learning from the noisy data, then obviously it is going to perform well on the training data, and it doesn't perform well on the testing data or on the unseen data. Then obviously we call it as a overfitting. So which performs well on training data and which doesn't which performs well on training data and which doesn't perform well on the testing data. And coming to the learning rate, so this is the other important factor which is going to determine at what pace the model has to learn. So if the model, the learning rate is low, as I had discussed with you in the previous slide, so it takes a lot of time for converging. And there is also a possibility like it is going to struck at the local minima or local maxima. So that is the other impact if the learning rate is lesser. And at the same point of time, if the learning rate is high, basically it is going to, the pace is very high. And there is a possibility that the model is going to overshoot, or else it is something like the model will start oscillating. What is the oscillating? In the sense, this is a very, very serious concern when we are working with the machine learning models. So let us assume when the learning rate is low, let us assume if this is a point which is considered to be as an optimal point, and now the model has to reach out. I'm sorry. Yes, this is a point, and this is a curve like this. If there is a curve like this, when the learning rate is very less, then what happens is, like, if it starts from here, slowly it comes here, and slowly it comes here, and slowly it comes here, and to converge over here to this particular point, it takes a lot of time. And somewhere, if it found something over here, then it confines this is an optimal point rather than reaching out the global best. It is going to struck itself in the local best. And the other scenario is like in case of higher learning rate, what happens is, like, it is going to take a bigger steps. When it start taking a bigger steps, so rather than stopping here, it jumps all the way from here to here. Then it realizes, no, it has crossed the optimal point, and again it oscillates back. So again it realizes that it has again crossed the optimal point. Again it goes in this direction. So it is something like it moves like a pendulum. So it oscillates like this, but it never stops at the optimal point. So that is the main problem when it is that is all about oscillation that usually happens when there is a higher learning rate. And after that, there is an optimizer. We usually have different types of optimizers that are meant for optimizing the gradient value. So one is a stochastic gradient descent. So basically, which is going to take the loss function into consideration, and then it is going to determine like what must be the optimal value. So which is a very widely used approach in the deep learning models. And the other one is a minimum batch mini batch gradient descent. So which works with the smaller size data samples. It really don't work with the entire data set. It only take a part of the data set, and it will start working on that. And the other one is a momentum based optimizer. So which is the advanced version of the stochastic gradient descent, which is going to take the previous network update into consideration in order to determine the current update. So basically, out of all these three, the momentum-based optimizer is one that is going to yield a better outcome. And stochastic gradient descent is the default optimizer that is being used in the majority of the deep learning models. Another thing is like coming to the activation functions, we all are aware of that. So like in order to decide whether the neuron has to be retained for the subsequent processing or to drop the neuron. So we are going to work with the activation functions. So one among them is a ReLU, so which is a very widely used activation function. So now here in ReLU, what happens is like when the input, the gradient value of an input neuron is a positive value, it is going to consider that. Or else if it is a negative value, it replaces the negative value with a zero. So resultantly, what is going to happen is like after few passes, the model might face a vanishing gradient problem that because of ReLU. And in order to overcome the vanishing gradient problem, they had started making use of the leaky ReLU, which is an advanced version of the ReLU, where instead of replacing the negative value with zero, that is what the ReLU is to do. For a positive value, it retains the same value. For a negative value, it is going to replace it with zero. But whereas in leaky ReLU, so for a positive value, it retains the same positive value as an input. And for a negative value, rather than replacing a negative value with zero, it is going to replace with some little non-zero gradient, so that that particular neuron will not be completely dropped from the network. So that in some cases, those neurons could be retained in the subsequent passes. And the other one is a sigmoid. This is not really a very widely used one, but when we are working with binary class problems, we are going to use the sigmoid, which is going to return as the probabilistic outcome in the range of 0 to 1. So it is something like at the last, we are going to have a softmax layer in the CNN model. So in the CNN model, like if we are asking the CNN model to determine how many number of, if the MRI image is having a tumor or not. So basically what actually happens is like it is going to give us a probabilistic outcome. So there is 0.82 percentage or 0.82 percentage like the model, that particular image is having a tumor, and 0.18 percentage it doesn't have a tumor. So or else it is something like what is the possibility that he would be placed in a service-based company or a product-based company. So 0.92 percentage possibility that he would be placed in a product-based company, and 0.08 percentage possibility that he would be placed in a service-based company. Then we are going to conclude that he will be placed in a product-based company, or else we are going to conclude that whether he's getting a diabetic, he would be a diabetic patient or not. Then it is going to return an accuracy of 0.85 percentage that he is non-diabetic, and 0.15 percentage he is a diabetic. Then we are going to come to a conclusion that the particular record is not associated with the diabetic patient. So like it is going to return as a probabilistic outcome. Basically, in that particular context, we are going to use a sigmoid activation function. So these are all the different hyperparameters we usually use, like the batch size at 4, the learning rate, or the optimizer, or the activation function, or the patients, verbose. So these are the different things that we are going to use for determining the performance of the system. And after that, these are the metrics that we are going to use to evaluate the hyperparameters, like the training loss, training accuracy, testing loss, and testing accuracy. Or we usually call that as a validation loss and validation accuracy. So here, let me complete it quickly because we don't have much time. So the first thing is that training loss. So training loss is like uh, so usually when we are making a classification, so for how many number of instances the model is going to fail, or like for how many instances the model is going to misinterpret with respect to the training data. So basically it is always designed to have the loss values to be minimal. It could be a training loss or it could be a validation loss. In either of these cases, with respect to the training loss or the validation loss, it is always desired to have the loss value to be minimal. And whereas coming to the accuracies, always it is desired to have the validation accuracy and training accuracy to be higher. So basically, there are some scenarios that are going to assist us to determine whether the model is overfitting or whether the model is underfitting. So usually, I will just show you an example where you could easily understand. So if we are going to have a graph that looks like this, in this particular graph, so for the training data, I will take the green color, and for the testing data, I was going to take the red color. So now on the training data, what actually happens is like, so we are going to give the data to the model, and then we are going to ask the model how well it is able to learn from the data. So and we are going to test it out, and we are going to just check for how many instances the model is going to fail, and basically we are going to use the when we are going to use the mean square error for regression, or else we are going to use cross entropy in case if it is a classification problem. So here what actually happens is like always the loss value would be like this. So here basically this the one that I had drawn here, it usually shows the uh training sorry, this usually shows the validation loss. Just a minute, I'll just show you an example. Now if the model loss is something like this, if the training loss is very lesser, and if the validation loss is comparatively high than the training loss. So in the sense, by seeing this particular diagram, we could easily say the model is performing well on the training data because the loss is lesser, means it is perfectly able to classify the training data. But when it comes to the validation data, it is not perfectly fine. There is a loss, there is a more loss here in the sense like it is misinterpreting. Then obviously we can say the model was overfitted. It is performing well on the training data, but it is not performing well on the testing data. And then similarly, the same case with the accuracy graphs as well. So what I mean to say is like when we talk about the accuracies, so if the training validation accuracy is something like this, and if the training accuracy is something like this, it is performing well on the training data, but it is not performing well on the validation data, then we can clearly say the model is overfitted. So basically, these are the four graphs that we usually use. Maybe in the next slide, you could see the images. Basically, underfitting and overfitting, I think we all are aware by this time. So I'm sorry, because we don't have much time, I couldn't emphasize more on this. So in case of underfitting, the model fails to perform well both on the training data as well as the testing data. But in overfitting, so it performs well on the training data, but it performs poorly on unseen data or on the testing data or on the validation data. So if you're going to see the graphs here, so if you're going to see the graphs here, these are the example for the underfitting. So the reason is that, so there is a significant gap between either of them. And that is one simple blind notation to decide the model is not perfectly fitted. And the other thing is like, if you're going to see, the model is performing well on the training data. So see, the training loss is less. But whereas the validation loss is very high. In the sense, this is one of the simple notation where the model is not properly fitted. Similarly, accuracies as well. So the validation accuracy is lesser and the training accuracy is more. In a sense, for training data, it is performing well, but for the validation data, it is not performing well. So this is one of the best example graph where we are going to see the model is not perfectly fitted. And I'll tell you what is the significance of this particular graph. As madam has Sujata madam has already told to you, I was an associate editor for a few journals, and a few of those journals are in top quartile, like they are 93 percentile journals as well. So I was an associate editor over there, and I used to get the manuscripts for the further processing. So what usually happens is like basically we usually pay for like the Springer, I not the Springer, basically the IEEE and the other things. They for few of the journals they are going to give the free access, and few journals they are going to pay for the reviewers as well. So there is a reason why the journal people, the journal office, what they ask the academic editors and the associate editors is to cross-verify the manuscripts before we send them to the reviewers. So if the academic editor or the associate editor doesn't feels like the manuscript is having a merit, we are going to make it as a desk reject rather than sending them to the review board. Because what the journal used to say is like they are paying like if it is MDPI, it is paying 50 to 100 CHF. So which is closely equivalent to 8,000 rupees. However, we couldn't redeem the money, but we people could use those vouchers for our subsequent publications in the same journal. The same case with the tech science as well. So I think there is something there. Somebody wants to write something on this. So fine, let me get back to the discussion. So what they do is like they'll be asking us to say like how well or they ask us the merit of the manuscript. Then what actually happens is like uh, the model is when the author says that they are getting 93 or 94 or 95% accuracy, but when we see these graphs, if the model is not perfectly fitted, then even if the model is getting 93 or 94% accuracy, there is a possibility that there is a data leakage. So in some cases, we are going to ignore and we are going to take we forward the manuscript to the reviewers. And even in some cases, the reviewers are going to point out the same thing. And basically, and here there are too many ridges. Like basically, I'll show you if it is a perfectly fitted graph. This is the way how the perfectly fitted graph looks like. So they doesn't have too many ridges and they are very close. So this is the way how a perfectly fitted model looks like. So basically, if this is the case, here there are no ridges and both of them are very close, and this is the way how the perfectly fitted model looks like. But here, if the ridges are very high, means basically the model is struggling to learn. So there is too much of variance in the input data. That could also be the reason why there are too many ridges over here. So anyway, this is a very good summary where people could easily conclude that the model is suffering with underfitting. And this is another example where the model is suffering with overfitting. So where like it is it is diverging. So sorry, just a minute. Uh, there is a small correction. I'm sorry. This is the graph for the overfitting. And this is the graph. I'm extremely sorry. This is a graph for underfitting. There is a small ambiguity in the title. So I'm sorry for that. But this is the graph for the underfitting, and this is the graph for the overfitting, where the model performs well on the training data, but the model fails in the testing data or on the validation data. And here, this other example where the model is going to perform well on the validation, and there is a significant divergence between the training and validation. So this is one of the example where the model couldn't learn properly. And one of the reason is like when there are lesser number of instances or if the data set size is small, or else in some cases, if the 50 epos are not sufficient enough, if it needs a 150 epos or 200 epos, even that is a case, this is the way how the graphs looks like. And I don't think even if here in this particular case, even if we are going to increase the number of epos, these two graphs will come closer. It won't come because there is an issue with the data itself. So this is the way how they are going to diverge. And this is the way how the perfectly fitted graph looks like. And that is the other thing. And after that, how we are going to fine tune the model. One is by making use of the regularizers. So for adjusting the bias and variance values of the model. So L1 regularizer or L2 regularizer we are going to take, and then we are going to use that. And the other one is a dropout factor. So which is going to determine what percentage of lesser significant features could be dropped from further processing is being determined by the dropout factor. And the early stopping mechanism is something like if you're going to see this previous graph, already the model has came to a saturation. Like they're going to ask after how many epos the model is being saturated. So by seeing this graph, we can say the model is being saturated somewhere close to at 20th epo, or else we can just make it as a 30th epo. And after that, the model has not learning anything. So because it came to a saturation. So if we doesn't stop at 30th epo, if we keep on increasing the 70th epo or 80th epo, then obviously it leads to overfitting. So basically, the early stopping mechanism is going to stop or hold the model when it reaches the saturation. In the sense, if it has reached the saturation, so here they are going to stop the model. They will not go for a 30th, 40th epo or the 50th epo. So that is the other thing. And this is the way how we are going to present the hyperparameters in our research articles. And this is the other way how we could also place a table like the number of kernels, the number of learning rate, the learning rate decay or dropout factor or optimizer, or what are all the things that we are using in the current study. We are going to make it as a table, and then we are going to present it to the readers. That is one best way how we are going to present the hyperparameters. And the other thing is like coming to the cross validation, there's other scenario, there's the other way how we are going to adequately assess the performance of the model. So because as I had told to you, we still work with the multi-layer perceptron with the categorical boosting, where either of them are not really well advanced models, but still then we are working with that and we are getting a better accuracy. And we might be getting a doubt like, is the model really performing well, or is there any sort of bias or something? Then this cross validation is one such mechanism that is going to assist us in knowing how well the model is working. I think it is now 7:30. I think I'm supposed to stop because maybe you people have to go for one more session. Quickly, if you're having any doubts in the things that I had discussed so far, you're open to ask me the questions.
Thank you, sir.
Yeah.
Dear participants, if you have any questions, please post in the chat box. Sir, already there is a question for you.
Yeah, ma'am.
How to optimize the hyperparameters by taking less time to train?
Yeah, yeah, that's a good question. Basically, frankly speaking, but just by seeing the model, we couldn't really determine, as I had told to you, like we had to test the model with 0.01 percentage and then 0.001 and 0.0001 or something like that. So that's all about making the statistical analysis or empirical analysis of the model. We usually in the title we write it as empirical analysis. So when we do that, we obviously have to test by just by seeing the data set or just by seeing the uh, something like the model, or in some cases the models might be having a default parameters, hyperparameters, but they may not be they may not be suitable. Again, we people have to rigorously try with different hyperparameters. Obviously it takes some time. Yeah, fine. Ma'am, anything else like anybody else or having some questions? I'm good to clarify. Some question is on k-fold validation. Basically, what actually happens is like there is a possibility of data leakage and all the people will start criticizing. So we take k-fold validation that is about to discuss. I thought of discussing that, but because of time constraints, I couldn't. Basically, what we do is like if k value is equal to 5, then what we do is like we are going to divide the entire data set into 5 partitions, and we use one partition for the testing and the rest of the 4 partitions for the training. So, and resultantly, what is going to, we just don't confine ourselves to k value is equal to 5. We test the model performance when k value is equal to 3, when k value is equal to 4, k value is equal to 5, k value is equal to 6, 7, 8, like that. Now, what happens is like when the k value is some x, so we will be using x minus one number of partitions for training and one partition for the testing. So in the sense like testing the model with a 50-50 split or 60-40 split or 70-30 split or 80-20 split. So that is one of the best example for the k-fold validation. It's k-fold validation when the data set size is small. Obviously, when the data set size is small, it itself is not adequate for training a machine learning model, then when the data set size is not adequate, there is no further question of uh, uh, working with the data set. Obviously, it leads to underfitting. So that is the reason why nowadays they're using GAN models for generating the data. And the other one is like sometimes we are going to use a class balancing like SMART or something for balancing. So that might assist us to get a better accuracy, but when the data set size is small, uh, it can't outrightly increase the performance. That is the other thing. And what is the role of validation data when we split the data into training, validation, and testing data? Basically, we usually the main mistake that we are doing nowadays, even the reviewers are pointing it out. The problem is like we are going to run the model only for one single run, and then we are simply concluding that we are getting 90% accuracy, 95% accuracy, or 97% accuracy. But the people and the reviewers are there seriously insisting us, why don't you run the model for multiple runs? So multiple runs means maybe you can use the same 70, 10, and 20 split, and you could run it for multiple times, and then you could get the multiple accuracy values, like multiple accuracies, multiple F1 scores, multiple sensitivities, multiple specificities, or multiple method correlation coefficient values. And we are going to calculate the mean of that, and then we are going to present it, which gives the appropriate measure of the performance, like the mean performance value, which is having a better model accuracy performance than running the model for a single run. So that is one of the recent trend that majority of the people are following. We people have to run the model for multiple instances. And how many k values should we take? Is it any fixed number? No, k value is not fixed. We are going to just check the model with the k value is equal to 2, 3, 4, 5, 6, and we usually take it up to 8 or 9. And some models, they are going to yield a better accuracy set when the k value is 7, and some models are going to have a better performance when k value is equal to 4, some at 8 or some at 9. And that is what we are going to write it in the conclusion. So we have our model, we had experienced that our model is performing well when the k value is equal to 5, or when the k value is equal to 6 in the conclusion part of the manuscript. Fine. Then if you are not having any doubts, I was leaving the session for your
One
next
second,
presentation.
sir, one second. Any more questions? Please, participants, post in the chat box. Okay. Okay, sir. On behalf of AICTE, Atal Academy, and SNIST, I extend our sincere thanks to Dr. Parvataneni Nagasrinivas, sir, for the insightful and technically rich session on this breast cancer analysis with explainable AI-driven CAT-boost multi-layer perceptron neural network. Sir, your session beautifully demonstrated how advanced machine learning models can enhance accuracy while maintaining transparency and interpretability. We truly appreciate your time, expertise, and commitment. The session has been immensely beneficial and has inspired our participants to pursue impactful research in explainable and trustworthy AI systems. Once again, thank you very much, sir. We look forward to your continued association in the future.
Yeah, ma'am. Thank you. Thank you for your time. Thank you all for your patience and all patience. And I'm extremely sorry that I was left with few minor things, but I think my session would be helpful for you all. Thank you all. Have a great day ahead.
Okay, sir. Thank you, sir. Dear participants, please stay back for the next session. We will start the session in 2 minutes.
The dear participants, so please note that no, we'll be having one exam tomorrow as per the schedule already, which is already given to you. So be prepared for that particular exam. Thank you all.
Okay, I hope I am audible. Good evening, everyone.
Good evening, sir. You are audible, sir. 1 second, sir.
Yes, yes.
Please share your screen.
Absolutely. Please give me a quick feedback whether you can see my screen, madam.
Yes, sir. 1 minute, sir. Your screen
Yeah,
is visible. Wait for 1 minute, sir.
Okay.
Welcome back to second session. Now, it's my privilege to introduce our session chair, Dr. Surajit Debnath, sir. Dr. Debnath currently is the Vice President, Institute Innovation Cell, Women's Polytechnic, affiliated to Tripura University, a central university, and Selection Grade 1 lecturer, Department of Medical Laboratory Technology. He has more than 20 years of experience in biomedical research and teaching. Dr. Debnath is a tech enthusiast and avid traveler. Dr. Debnath have participated in various academic works in institutions of Europe, in Germany, Denmark, and UK, besides in premier Asian institutes in Hong Kong, Indian labs such as AIMS, Cytogenetics, IIT Kharagpur, Biotechnology, IIT Guwahati, Biomedical Engineering, NBPGR, Plant Genomics, etc. Dr. Debnath is the recipient of Young Scientist Award from different agencies, DBT, DST, and CSIR, and recipient of Tata Trust Grant for CME course in Royal College of Pathologists, London. Reviewer of several Scoopers SCI indexed journals published by Elsevier, Springer, Biomedical Central. Along with regular academic activities, he is also engaged with several biotechnology companies in northern and western India as a consultant. He have conducted various workshops and talks, acted as senior chair in international conferences sponsored by national and international academic agencies. He delivered numerous invited talks in national and international academic gatherings. Currently, he is guiding a group of international students for their internship from Russia, Turkey, and West African countries. Dr. Debnath filed 2 patents in India on biomedical research. So over to you, sir. Please commence the session, sir.
Okay, thank you for the introduction. I am also thankful to Atal, the concept of AICTE Atal FDP, where multiple different people can, from different this thing, schools of thought, can interact among themselves and develop the whole ecosystem. By saying so, I hope I'm clearly audible. So we'll have this thing on how the medical imaging is important for critical care, not only that, for overall patient care and safety, and eventually what are the problems related to this thing, distortions in medical images, and what are the different methods to denoise these particular things. While doing so, we'll also demonstrate 2 tools. One, we'll be giving you an idea that how exactly the developments in denoising methods and techniques has been developed over the years in an interactive fashion, and then we'll try to do a little simulation based on the established methods for medical image denoising. Now before that, my domain is biomedical research, and therefore we are interested in particular those things. The application, the application of these developed tools we are more interested in, rather than developing the tools ourselves. So one more aspect of our studies that we are doing is to develop digital resources for smaller companies. For example, there is a
Sir,
company.
sorry for the disturbance, sir.
Uh-huh.
Can you please just increase the audio of your audio, sir? So you are not so audible. Just increase the voice, sir.
Okay, so our interest is mainly on the application part
Yes, sir.
of
Now
this,
it's perfectly fine, sir.
the application part of this, the established methods and newly developed AI/ML methods for denoising of medical images, which brings about a lot of these things to the ultimate clinical result. So our interest was on those things. While doing so, we have collaborated with a small edutech company who are in the business of teaching smaller classes or some school students on the new digital tech. They are doing robotics as well as this image processing stuff. So we have developed 2 different tools for this particular company, and we have also handed over those things to them in a partly commercial venture, and we'll demonstrate those 2 tools to our participants also. It will not be highly this thing, but it will be highly interactive, and it will make the whole experience very lucid for the students or the smaller students. For example, a student of computer science or whatever is now joining the first year or second year of this thing studies. So how he or she will be this thing understanding the whole concept of medical images, noises in those images, and to denoising of those images, what is the ultimate result, everything they will understand, and this thing by these using these tools. The tools are completely built up in our lab, and our brandings are also available on that. So why denoising of medical images is needed? This is also very interesting question to understand. So comprehensive research analytics on medical image denoising is critical to objectively benchmark algorithms, ensure diagnostic reliability, which is very important, because in medical diagnostics there is no ifs and buts. there is no gray or there is no fuzzy logic working on it. It must be either yes or no. So in those cases, no, it's a huge burden on the developer or the caregiver or the doctor or the clinician or the whole ecosystem to do the diagnosis in a perfect way. So what happens as the medical care treatment is the cost is increasing day by day and the inflation is very high in medical care. So the patients are also very much particular that since they are paying the money, they should get the world-class treatment as well. So ensure diagnostic reliability is very important, and accelerate safe clinical translation across diverse image modalities. So this is also very important aspect of denoising of medical systems. These images, these text and everything is made by our lab and for internal purpose uses only. So why different imaging techniques are needed? This is also very interesting in this thing to understand. So we will be talking about 4 different techniques: X-ray, CT scan, MRI and ultrasound. So why these are important? These are very important question in the beginning itself. So X-rays are used for bone fractures, chest infections and different types of arthritis where there is a structural change, a massive gross structural change. These are the uses of X-ray, and the indications are broken bones, pneumonia. In pneumonia, what happens? The lungs undergoes severe fibrosis, and therefore the comparison between a pneumonic lung and a healthy lung is very prominent and very very sound, and therefore these X-ray, despite of the fact that it is not very precise, but it is helpful in these cases. Joint problems where there is a degradation of the coating material on the bone surface. In those cases also X-rays are very good. Then comes CT scan. Now in CT scan, far more detailed images are possible by slices, and therefore a 3D understanding of the construction of the organ or the soft tissue is also available in CT scan, which is not possible in X-rays. So you can't get a 3D idea, despite of the fact that these images are in slices, but it will give you a 3D idea of the whole system. As you can see, internal injuries, this is very important. Tumor detection, first and foremost, computational tomography was devised for tumor detection only. As we know that basically tumors are of 2 types, one is benign and one is localized, which is malignant and benign. So benign tumors are localized, but the intensity of the distribution of matter is usually similar to the normal tissue, and therefore many a times it has been to differentiate between a cancerous tissue and a normal tissue, where CT scan gives a clear cut idea whether there is a internal injury as well as some tumor has been developed. By and large, CT scan can only identify benign tumors, that means localized tumors. So what are the indications? Some head trauma, internal injuries, that means if there is some aneurysm or internal bleeding in the head near the brain, which is very sophisticated tissue. So an abdominal issue, for example, if there is some kind of gross abnormality in the liver or GI tract, some kind of this thing such as inflammation in the pancreas, inflammation in the liver, or some GI tract infection, large scale, massive infection, those things are been nicely detected by CT scan. Some internal cancers, as I have already mentioned, not malignant cancers, but by and large localized benign cancers are nicely detected by CT scan. And one more important aspect is multiple different brain issues. For example, there is a thing called multiple sclerosis, in which what happens, brain undergoes a sequential degradation of the tissue. Those things can also be identified by means of CT scan. These days CT scans are also used to identify very minute changes in the brain structure in cases of epilepsy then what do you call is this thing multiple different brain related this thing where necessarily no hemorrhage or no trauma is there. These are some very minute structural changes. Those are also been identified by CT scan. Then MRI is the highly advanced imaging system, by far the most advanced imaging which gives you a complete detail of soft tissue, brain, spine, ligament, disc, you name it, it have it. So every and each detail of this thing, soft tissue architecture can be detected by MRI. It can also identify subsurface area cancers. Those cancers which are very difficult to detect by CT scans are usually detected by MRI. Ultrasound is a completely different ball game altogether because it uses a different kind of technology. And it uses in pregnancy monitoring, abdominal checks, fluids. Fluids can be nicely means fluid in a this thing like a prostate, fluid in a urinary bladder. So how much urine has been collected, those things, and how much is the this thing what is the amount of fluid present in the fallopian tube during the pregnancy, everything can be identified by ultrasound, and it's very safe. What are the indications? The indications are fetal development, then gallstones. If there is a sudden change in the intensity of the liquid, where there was a liquid, all on a sudden some solid has been built up, those areas are very good to this thing by ultrasonography. So these are the common uses of these things, and now we will talk about a bit about how these modalities work, how X-ray work. So X-ray tube emits X-ray, which is this thing, the differences of the intensity of the X-ray is based on air, soft tissue and bone, and eventually a characteristic this thing pattern emerges on the silver bromide coated photographic plates, and which eventually gives you the gross these things of the internal hard tissue, not the soft tissue, hard tissue. Lungs is also a soft tissue, but there is a this thing called the covering of the lung is such that it have some characteristics of the semi-solid tissue, and therefore lung is also very much visible through this thing, but not other things. For example, you cannot see liver, you cannot see pancreas, you cannot see your what do you call internal female reproductive systems or male reproductive systems through X-rays. So these are the limitations. So X-ray tube emits specific this the intensity of X-ray, then X-ray is absorbed by the hard tissue, and eventually an image is generated. So what are the noises which interferes in the X-ray plates? So the noise type is known as Poisson electronic noises, which is where the signal to noise ratio is approximately 20 to 30 decibel. The primary source of the noise is the quantum noise. And the clinical impact is very, very high, because many a times what happens now, minute fractures which eventually leads to some kind of fatality, even development of cancer, cannot be identified these what do you call X-ray images due to these the different sources of noise, which reduces the signal to noise ratio to a significant extent. So quantum noise which has been generated will impact in 4 different aspects. Diagnostic accuracy will be reduced, then mitigation techniques, so eventually it will also lead to wrong diagnosis or less or high diagnosis. The significance in low dose means many a times it has been seen that for kids exposure to this thing is very there are some contraindications in X-ray exposure. So low dose imaging is not very good at this thing in X-ray. So therefore there should be some technique to reduce these noises. We'll come to those points later on. So computer tomography, how exactly it works? If we can say that in CT scan also a kind of X-ray is used. It is similar to X-ray. It is nothing but an X-ray only, but only the this thing is the detector as well as the source of the X-ray are rotating, and therefore gives a three-dimensional idea of the internal tissue in a better way. Here the detector measures absorbed X-ray particles and eventually generates a what do you call X-ray kind of image, where the internal organs are slice by slice taken. These X-rays are slice by slice, and therefore if we study all the slices, we can have an idea of the three-dimensional architecture of the tissue. Due to the rotation of the signal as well as the receiver, we get a 3D image out of this particular modality. So the noise type is again Poisson, and the typical this thing is comparable to this thing, what do you call, X-ray only. 25 to 40 decibel is the typical SNR, and then the primary source of the noise is the photon counting statistics, the internal computer which counts these photons. Are the primary sources of the noise. The clinical impact is medium because by and large it gives superior image than this thing. X-rays also it gives a 3D idea of the internal soft tissue, and therefore the clinical impact of this noise is not very high. Now what it will lead to, the photon counting statistics leads to an image intensity variation, because the same tissue in repeated CT scan, it can have that the identity of the same tissue many a times may be altered due to photon counting statistics malfunction, and eventually it depends on the clinician who will look into this thing, because the doctor will finally decide whether the cancer progression has been reduced or not. So we should understand one thing. Many a times these modalities are not for diagnostic purpose but also for prognostic purpose. What is prognosis? Prognosis is how the therapy was affected or not. For example, a patient who is suffering from some kind of internal trauma has been under treatment for let's say 3 months. So after 3 months the doctor once again said that okay, you go and take one more CT scan, so that I'll compare both the slides and eventually let you know whether the therapy is okay or not, or shall I change my opinion as well as my drugs. That means whatever medicine I am giving, shall I change it or not. So those things are also used. These diagnostic modalities are not only diagnostic, these are also prognostic. So it will help the clinician to understand whether the therapy is working or not. Therefore image clarity is a very important this thing, and which leads to altered diagnostic accuracy, and therefore it may compromise the patient care, and therefore there should be have this thing is sufficient this thing to reduce this Poisson noise in CT scan plates. Then comes to magnetic resonance imaging, which is a high-end therapeutic modality with excellent outcome, and everything is very good at this. I'll this thing explain it later on. The human body and hydrogen atom are in interplay. So body is made up of hydrogen atoms which is with spinning protons. So what the magnetic field does, it destabilizes the protons inside the internal, throughout the body. It will destabilize the proton, and eventually when the radio frequency pulses pass through it, they once again come back to their original place of this thing, and therefore the change is detected by the photon detector, which eventually give rise to a signal which is very precise and perfect, and therefore you can see the image is most perfect, and very minute details can also be identified by means of this MRI. And therefore malignant cancers, that means for example cancer in the bone marrow, or let us say liver cancer, which is soft tissue cancer, and can be nicely detected by this MRI scan. So where there is some opportunity for mistake in CT scan, MRI reduces that possibility of this thing wrong diagnostic to several fold due to its superior imaging capabilities. Despite of it, there is some amount of this thing noise which is mainly known as Rician noise, and The source of the noise is the thermal noise in the coils, which are being used for the magnetic resonance. The typical signal to noise ratio is approximately 15 to 40 decibel, and the clinical impact is very high because it is used only in cases where rest of the other modalities are not useful. In that case, if the Rician noise is highly impactful, it reduces mm, the mm, the diagnostic accuracy to several fold, and eventually the patient care will also be compromised. And therefore there should have been sufficient studies going on in conventional methods as well as in advanced methods to reduce these noises in this thing. And last and not the least, the ultrasound imaging, how it works. It works on sound waves. The transducer sends high frequency sounds. The sound waves reflect off the tissues, for example bone, soft tissue as well as fluid, and eventually the same handhold what do you call handheld device will also integrate the sensor, which will identify these echoes and converts it into the image. The image formation is safe, non-invasive and radiation free. So ultrasound process is how it generates echo, and then it passes through the tissue, soft tissue and hard tissue, and eventually generates an image. So if you can this thing remember that if we have started from this X-ray, the X-ray is highly red in color. In comparison, the sonography is completely green in color, means this is less invasive and highly safe, even safe for the unborn child. As you can know that a child under some particular age should not go to the X-ray machine as well. MRI is despite of it safe, but there are some contraindications. I'll come back to those points, and later on we'll go to the denoising protocols. So what are the noise type? The noise type in ultrasound is speckle noise, which is due to the coherent interference. That means the signal that is projected towards the tissue as well as the what do you call the sensor which will receive the echo are set in the same this thing area, and therefore some coherent interference is there, and which causes for the typical SNR of 10 to 25 decibels. Now there is an interesting snippet. So in our lab, what we are trying to figure out is we are trying to figure out that whether we can generate a digital platform to understand or to study these important aspects of biomedical imagery in a very lucid manner, and therefore we have developed a tool, not one tool but two tools, which will help smaller students, small class students, for example first second year students, even school students, to understand that how this medical imaging works, and what are the problems with these what do you call the noises in the medical images, and how these denoising technologies work, and that also is a very integral part of our solutions. So we have recently collaborated with a company which teaches robotics as well as multiple different biomedical aspects of in school students as well as young college kids. And we have built two tools for this company by using the recent modalities, that is artificial intelligence and machine learning. So for designing these tools, we have had a good number of meetings with the company, and we tried to understand what exactly they want, and eventually we have build these devices, not devices, these digital solutions for these companies. The one company is already rolled in, and the other company, these are small companies of Eastern India. Despite of it, it's a good revenue generating stream for our lab. So first of all, we'll have a discussion on the comprehensive analytics on medical image denoising. What are the studies that has been published from 2015 to 2025? So what we did, we have made a interactive digital platform to understand this whole concept of medical image denoising and how these are impactful. So quickly we will have a demonstration on this, and then eventually come back and show you that how exactly on which principles these tools are based on. So we are interested in the application part of it, and we'll I'll stop sharing now, and I'll once again reshare my desktop once I start this tool to give you a demonstration to understand that how exactly medical image denoising can be used for teaching learning purposes. Just give me little time. I'll just okay. Okay. Just hold on. Yeah. Okay. Okay. Madam, just give me a quick feedback whether my this thing desktop is visible to you all.
Yes, sir.
Okay. So this is our home page of our lab. So what we are collaborated with multiple different organizations as well as companies. So our resources is on denoising is just hold on. Okay, not in this page. We'll go to the other page, which is just hold on. Okay, I will go to Explore Research tab, and yes. Okay. Okay. These are different tools that we have built for our these things. Just hold on. Yeah. Just hold on. I'll mute myself. Okay. Yeah. So yes. So this is our tool. So comprehensive analytics on medical image denoising. So whatever development has taken place in last couple of years, we'll be demonstrating this in a comprehensive way, so that it can be used for this thing also. You can use this for your research studies as well as for teaching to your students as well. Okay. So once you click on this learn more button, we'll go to a other website, and yeah. So as you can see, this the branding of our lab is also prominently there, but once it's given to the third party, their branding will be available here. So medical image denoising protocols, and data from 150 peer reviewed studies has been used in this. In the study period is 2015 to 2024. 4 different imaging modalities that we have already discussed are been incorporated. There are some other imaging methods, for example DEXA scan. DEXA scan is a scan which is usually done to identify the the age of a person, or the what do you call is bone deformity. For example, if there is a thing called vitamin D deficiency, and then bone fractures, and those things are not an X-ray. It's a different kind of this thing which identifies the density of the bone. So that scan we have not incorporated. And then some more some positron emitting tomography is also there. PET, we have also not incorporated that thing in our this particular tool. The main tools we have incorporated. Total 8,740 research papers has been analyzed, which were sourced from PubMed and IEEE, highly this thing dependable sources, and some the 127 architecture on different digital learning models has been analyzed. The average increase in the signal to noise ratio improvement was been plus of 5.8 decibels. That means without implementation of the tool and after implementation of the tool, the average in these 8,740 studies has been approximately 5.8 decibels of increase in signal signal to noise ratio increment. So out of that, 77 are clinical studies. So these are very important. Why? We had to incorporate some classical theory based studies as well. But out of that, we identified that 77 clinical trials are there. Clinical trials are those which are not in paper. You have to, for example, this thing paper has analyzed that they have used naive Bayes algorithm or probabilistic classifier algorithm before and after the images, how the image quality has increased, and they have applied the same thing to the patients. So these 77 studies we have focused more to make this whole this thing interactive, this thing what they call website. So the noise characteristics by imaging modality that we have already spoken about. The research publication trend, if you see now, classical methods has been diminished. So 2015, if we go, these classical methods of classical methods have been reducing. Okay, so for example, Gaussian filter and such classical things has been reduced. But on the other hand, if you can see, deep learning algorithms, applications of deep learning algorithms has been significantly increasing, and therefore in our discussion we'll come back to these things also. The basics of artificial intelligence, machine learning, and those things we will also have a discussion on. So research publication trend is also been generated here. So as I have said, these are interactive databases. So if we click on this classical method, so we'll discuss the classical method now. What are the classical methods that has been used? So Gaussian filter, median filter, bilateral filter, non-local means, wavelet functions, hard and soft wavelet, then anisotropic diffusion. These are some of the classical denoising methods that has already been in use. And therefore, if we can compare these things, we can see that increase in the signal to noise ratio has been this thing 28.5, where SSIM is 0.78, and subsequently if you hover on each and every this thing, this is not a normal spreadsheet, but it's an interactive one. As you can see here, it becomes much more interactive for the students you are teaching, and it will be very helpful for the students also to remember these concepts. Because as you can see here, it is not some static data that you are working on, but whenever you hover on something, it changes its pattern, and therefore it gives an excellent this thing. You can communicate with your students in a nice way while you are teaching this particular thing, the classical deionizing methods and their performances over the years, and these are all from peer reviewed data. Then we'll compare it. Let us compare it with machine learning and deep learning methods that has been used for this. this thing, what do you call, the similar kinds of this thing. So here what we can see is each and every time we hover on this, we will see that the PSNR as well as SSIM is much more than that of the classical methods. For example, this one here, it is 33.4 decibel increase. So in classical method, no, it will be very difficult to find something more than 30. The non-local means are 30 and the rest all are less than 30. But in deep learning method, you will see that how good the method is. 33, here is 32, there is 33 again, then 33 decibel, then this 34.2 decibels, then that 32.5 decibels, and then 31.8 decibels, and then here it is the highest, that is 34.6 decibels of increase. So here we can do the performance comparison between these two modalities. So what are the methods they have used? The robustness in classical studies is 80%, means you can do these studies very rapidly. But in machine learning, the robustness is bit reduced. But edge preservation, if we see the medical images, classical methods, only 65% edge preservation is there, whereas in machine learning applications, the edge preservation, I'll demonstrate one more tool to make you understand what is edge preservation. In machine learning, it is 78%, whereas in deep learning algorithms, once we use the studies which has reported deep learning algorithms for edge preservation, 92% increment can be seen. Again, for texture detail, if you see classical methods, only 58% studies show increase, whereas in machine learning and deep learning, the increase in texture detail are much more. The before application of the filter, the texture detail was not much, but after the application of the filter, texture detail was been increased to a significant extent. Now here, artifact reduction, we will demonstrate what artifact means for a medical image. In artifact reduction, the classical methods are only 70% useful, whereas machine learning and deep learning are significantly increased in their capabilities. So these are all interactive this thing, and as you can see here, these are highly this thing data, reliable data. You can not only generate research paper out of it, you can use these images as well for your research purpose. And here is the clinical value.
Sorry for the interruption, sir.
Yes.
Sir, please increase your volume, sir.
Okay.
Participants are requesting.
Okay, sure.
Yeah.
So I have very less idea that why this volume problem is coming. So in clinical validation, if we see, so as I have said that brain MRI tumor, what happened, the quality of improvement by using machine learning and artificial intelligence based filters has been very high. The quality improvement is approximately 18.5%, and diagnostic accuracy increased at 94.2%. So in brain MRI tumor, so in MRI these things, MRI slides, when these machine learning algorithms has been used as a filter for the denoising purpose, this has been the report. And then if we come to the chest CT nodule, so what happens in chest, that means in the lungs, many a times these nodules will generate. These nodules initially will be localized cancer, but eventually they will turn into a malignant cancer with life-threatening conditions. And therefore, this chest CT nodules was a very good candidate for denoising purpose. And by using machine learning and deep learning method, quality improvement was 22.3%, as well as diagnostic accuracy increased 91.8%, which is a significant jump in diagnostic accuracy by means of denoising. Here, cardiac ultrasound. So cardiac ultrasound is usually known as this thing, echocardiography. So cardiac ultrasound is not similar to, the technique is similar, but the reading and the instrument as well as the software are different for echocardiography. In echocardiography, mainly what we look at the ejection fraction of the heart. That means whether the heart is sufficient enough or capable enough to eject the amount of blood it should eject at per unit time interval. And one more thing which is very important in cardiac ultrasound is the structure of the valves. So valves are basically one-way valves which projects the blood from the heart to the body, and also takes back the blood from the body to the heart. So though the architecture of the valves as well as the ejection fraction are the main components which are being observed by cardiac ultrasound. And it has been seen that the cardiac ultrasound image quality has been significantly increased by means of deep learning algorithms, quality improvement up to 15.7%, and diagnostic accuracy increased up to 88.5%. So this is very important. Then mammography. Mammography is nothing but to identify breast cancer in females. Again, a very critical thing for what do you call is medical imaging, where the soft tissue undergoes rapid changes once the cancer sets in. Eventually it gives no time to respond if it has been spread to other tissues, and therefore just hold on, and therefore this mammography is a very important diagnostic modality which is based on sonography only, means sound wave based this thing only. But it has been seen that the deep learning algorithms have increased the quality to a significant extent to 20.1% with a diagnostic accuracy of 92.3%, which is very, very great. Subsequently, knee MRI. So many a times due to our altered lifestyle and multiple different things, the burden of the body is placed on the knees, and many a times the knees undergo rapid degradation, and therefore the cushioning effect of the knees between two knees, between the femur and the knee, there is a cushioning effect which reduces the friction between the two bones. Other than that, the bones are nothing but the minerals. For example, in your vehicle, in your automobile, if you do not put the lubricant, what will happen? The machine will cease to run. Because what happens? Because these are highly mechanical adjustments, lubrication is very important. So day by day this lubrication reduces, and which is significantly visible in terms of MRI. A small reduction in the lubrication leads to significant distortion in the knee, and therefore knee and MRI is an important diagnostic modality for patient care purpose. And it has been observed that by using deep learning algorithms, quality improvement in noised and denoised MRI scans are very significant, which leads to a diagnostic accuracy of 89.7%. So as you can see here, these are highly interactive tool which makes the teaching learning process very interactive as well as very streamlined for persons who are coming for the first time. As you can see here, the ability of the system is also very robust. We have studied 8,740 research papers. Out of that, 77 are clinical trials. That means the trials which are integrated by companies like Siemens, or in India BPL is there, which is using these denoising technologies for their digital imaging devices. So this is a highly interactive tool that we have developed in-house for one of our customer, where we are also cross-selling this to the other collaborator of us who is mainly into robotics. So coming back to the PPT now. Okay, and then from the current slide. Okay, so that was the comprehensive analytics on medical image denoising to give you a bird's eye view. So now coming back to these deep learning algorithms and machine learning algorithms, how exactly do they work? This is very important to understand. I hope my sound is visible, audible now. So basically the prediction algorithms works in these three particular what do you call systems. One is classification, another is regression and clustering. These are the basis of prediction algorithms, because no, in denoising also a significant amount of digital learning is expected. And these days when generative AI is in full force, the increment in the denoising ability has been increasing day by day in a significant manner. So these denoising many deep learning algorithms uses tools like unsupervised learning algorithm as well as supervised learning algorithms. So unsupervised learning algorithms are similar to, as all of you already know. For example, my younger kid is such that if I tell her not to put her finger on the flame, she'll, despite of it, put her finger and then learn. So this is kind of unsupervised learning kind of thing. What we'll do is we'll do a little hands-on. Um, uh, Mainly for our participants who are not from data science background, it will give you an idea that how prediction algorithm works in a very simple lucid manner. So what I'll do is I have made one prompt. I'll share the prompt in the chat box. You can also paste the prompt in your this chat GPT, and it will deliver a downloadable file to you, and you can do the hands-on with me. So it's a simple hands-on. What we'll do now, I'll do this. I'll where is this thing? Chat box. Yeah. So in the chat box, what we'll do is, oh, very sorry, there were no voice at times. Very sorry. So this is this thing. The prompt you can use, participants, if you want to see to make a lucid understanding of how this thing what do you call is this thing works, what this prediction algorithm works. Okay, so we'll copy this and go to chat GPT, and I'll paste it to chat GPT, and what it will do is it will generate a Excel file for me. It's working in the what do you call background and trying to figure out. You can also do this thing. So what we given the prompt is to generate a downloadable Excel file with two columns. One column signal to noise ratio in a medical image is a hypothetical this thing Excel sheet, and it is taking so much time. Madam, I am audible, right? Okay.
Yes, sir, you are audible.
Great, great. So the downloadable file is there. We will download it right away.
Sir, it is better to increase the volume, sir.
Okay, okay, okay. What we'll do is we have pasted this prompt to the chat box. That means this and what? Just one second. It has generated a downloadable Excel file. So we'll open the Excel file, all of us. I hope this thing is also visible, and the screen is also visible. Okay. Okay. Yeah. So this Excel file has been generated by this engine. Here there are two columns, one signal to noise ratio and another precision in diagnosis. So what we'll do is we'll try to figure out what is the effect of signal to noise ratio on precision of diagnosis. Okay. So what we'll do is we'll select these two columns. Okay. Participants can also do if they want, and then go to insert box and then do an XY scatter. Okay. Now this is an XY scatter. Okay. So what is there is the relationship between signal to noise ratio in a medical image and the diagnostic this thing precision is in y-axis. So this is the relationship. If the signal to noise ratio is increasing, that means signal is increasing rather than noise, because it will lead to high precision of diagnosis. Now consider that now consider that you have please try to understand, you have designed an algorithm, or you have identified an algorithm where the signal to noise ratio is been let's say 23.6%. Okay. Now you want to see what will be the precision in diagnosis. So how you will determine? So you have to predict it. So we'll see how prediction algorithm works, and it will give you an idea that how prediction will help. So what we'll do is the graph has been prepared. Now we'll click on any of this thing and then add a trend line. Okay. Now the trend line will be this thing. We'll add the linear trend line for making the calculation easy to understand for our students. Okay. So I am giving this demonstration in a student centric view, which will give our students a learning experience a better this thing. So display the equation on chart. We will click on this and then close. So what we will get is we will get a straight line equation of y is equal to mx plus c, where y is the precision on diagnosis. Okay. So we will calculate, consider that, as I have said, that let's say the signal to noise ratio in your model that you have built is approximately, let's say 23.65. Okay. 656 is the signal to noise ratio in your model that you have built for a, let's say, MRI, or let's say for a CT scan image. Now you want to understand that how it will impact the precision in diagnosis. Okay. So in order to understand that, what we'll do is we'll put this x, that is x will be this thing 23.65, and we will do a quick calculation here. As you can see here, so it is 0.76 multiplied by this, and then okay, put it in a bracket, then plus 53.4. So by using this data set, now this is a data set of existing literature, consider like this. So this is a data set from an existing literature, which gives you an idea that signal to noise ratio will be like this. So you have identified a model where the signal to noise ratio is 23.656. By using this equation, you can figure out that the precision in medical diagnosis will be 73 or 71.3%. So this is how prediction algorithm works. Okay. So we'll come back to our the slide. So I hope you have made this thing to it. So what happens is there are some latent space in this deep learning algorithms. These are the deep learning algorithms which you are already aware of it, and why these generative AI models are very important these days. There is a little discussion about it. Now coming back to our second simulator, we named it as SEMA, or Simulator on Image Signal Denoising for Medical Analytics. So we have studied only 1 year data, and we will try to figure out how these different denoising techniques will be helpful for increasing the details in the medical images. So for that, again I'll be going to my tool where, yes. and then we'll show you that how this thing will work. So as you can see here, this is the simulator on medical image signal denoising for medical analytics. Okay. Okay. So advanced image signal denoising simulator for medical analytics utilizes cutting edge algorithms, already established algorithms, to enhance medical image quality, improve diagnostic accuracy, and support precision medicine through sophisticated signal processing techniques. So what we did is we built one digital platform which will help your students to understand different modalities of what do you call denoising methods for medical images. Okay. So my background is biomedical research, and therefore I am very interested in this particular application purpose rather than the developing the whole tool by myself. So this is the simulator. This is the simulator. Okay. Just hold on. Yes. So the simulator on image signal denoising for medical analytics, as you can see our branding is already there. So advanced noise reduction techniques for MRI and CT scan. So we are not using the other two methods. We will be using these advanced methods only, and we will try to figure out that how these tools will be used. So what you can do is, as I have said, that all our tools are highly interactive in nature. So you can change the image type as well. So brain MRI or CT scan of chest. Both of these two methods you can do. So first of all, we will be using brain MRI to study the whole exercise. Okay. So now you can even configure the type of noise you have. Okay. So we have used these 4 different types of noises. One is Gaussian noise, another is salt and pepper, another is speckle noise, and the Poisson noise. So 4 noises with a tool to increase or decrease the level of noise. Okay, can you see it? Yeah, you can increase the noise. Means what? You are changing the signal to noise ratio. At the same time, you can also use these denoising methods. Okay, and the quality matrix will be given by means of PSNR and SNR. So filters are also 4 types. We have used the conventional one, and the advanced one we will be doing in the next couple of weeks, and we will be giving it to our this thing collaborator. So we can even collaborate with any of the participants if he or she want to build one digital tool for their study purpose. And the 4 types of this thing that we have is the we have shown you, and then this is the image. Okay. We can do the whole animation directly. Okay, so you can put it like this, animate, just hold on, and this is the noisy one. Okay, this is the original one, and this is the original image. As you can see, this is what, this is brain MRI. Okay, this is the brain MRI where you have put the filter of noise at a 35%, and you have used Gaussian filter, and we will increase the strength of the filter now. Okay, so let us do it more than this. So the filter strength is 8. on this thing of 8 to here it is 20. So once we click on this filter and then denoised, what we see is just hold on, this is the noise, this is with noise, and as you can see here, so what are the things we have put the noise how much 35%, and now we'll denoise it. Okay, after denoising, as you can see, this also shows you the disadvantage of Gaussian filters. As you can see, the noise in the periphery has been reduced to a significant extent, isn't it? Can you able to see? The noise has been reduced to a significant extent. So this was for brain MRI. So again, if you want, you can take a screenshot of it. So let us say first of all the original one. This is the original one. Okay. Then this is the noised one. Okay. And this is the denoised one. Just hold on. This is the denoised one. Can you see? So noising has been the noises has been reduced to a significant extent. So likewise, our collaborators can change the filters and hover around these bars, and eventually they'll able to demonstrate their students that how these different types of filter uses their abilities to denoise the medical images. So it's a hypothetical screen. We have not used any real MRI data set. So now we'll go to brain CT scan. So when we go to chest CT scan, we'll see the structure has been differentiated different way. Okay, so we'll go to the original one. This is the original chest nodule. This is the chest nodule hypothetical figure, and this is the original one. Let's see the denoised one. Oh, sorry, the noisy one. This is the noisy one. This is the noisy one. Can you see? This is the noisy one, and this is the denoised one. Just hold on. This is the denoised one. Okay, but we are keeping the same this thing. We are putting the Gaussian noise and Gaussian filter and place that here at 6, and the noise level is 35%. Okay, so likewise what we can do is, there is a description of the Gaussian filter as well. If you want to add some more additional filters and all, you can definitely contact us. We will able to generate this digital tool for you, so that your teaching learning process becomes much more streamlined and lucid and student friendly. So this is the second tool that we have developed. Okay, so coming back to our presentation. Okay, so these are some recent collaborations that we had. Not very recent, but some old collaborations are also been shown. By saying so, if there is some for discussion, we can have a discussion. Or if you want, you can go for the demonstration all over again. For example, just hold on. Yes, this one. In this one, we are about to integrate this data set based this thing. We'll also add more buttons over here. As you can see, the noise overview, then classical method, machine learning and deep learning methods, performance comparison, clinical validation. We'll add one more button here, in which we'll also have to give the students an idea that on what basis these things are detected. For example, we will incorporate these informations here, to make it more lucid for them. Okay, they need not to open the PPT at all, but from the tool itself they will learn all these details, which is safe, which is non-invasive, much more, all the types of noises, what are they are, what are the impact of these noises in these particular modalities. Each and every detail will be there in the fingertip. So it will be very this thing for our participants, for the students, to understand all the these things in a nutshell, from MRI to this thing. All these things will be integrated from this particular thing. So what are the contraindications of imaging? This is also okay. I have not discussed it. I think I have not discussed it. So this is very important snippet again, that there are some contraindications of X-ray. The contraindication of X-ray is pregnancy and pediatric patients. Okay, so you cannot use X-ray every time, and therefore all these modalities are there. Then the CT scan. So there is high radiation dose. Again, pregnancy cannot be this thing, and many of you already know that in CT scan, one barium chloride this thing injection is given, which acts as a electron denser. That means it will act as a dye for CT scan. If the contrast is needed, the injection is given. If the contrast is not needed, injection is usually not given. Now that injection, no, that means the drug is very dangerous. Means after giving the this thing, many patients have either was not ready to go further with the CT scan, or started vomiting, or many have resulted into palpitation also. That means bradycardia. That means they have increased heart rate, because no, it gives a very bad taste. Even in the mouth also they will feel. I have spoken to persons or patients personally. A metallic taste will come in this thing, and 2-3 days they will not able to eat properly. But the patient compliance is very bad. If a patient who have already done a CT scan with a contrast, if you tell him or her that do you want the contrast or not, despite of it there is no choice. If the doctor want the contrasting image, then he have to comply. But nobody wants a bad taste or this kind of nausea during in a critical this thing, because CT scan is not a simple X-ray or simple sonography. It's a very critical method. And kidney problems, contrast dye. This contrast dye is very this thing. Before CT scan, you should also go for a blood test. The blood test will determine whether your GFR, that is glomerular filtration rate, is okay or not. If it is not okay, the doctor will not tell you to this thing. Go for this this thing. What do you call is? It will. Okay, it will. The doctor will not tell you to go for this this thing. What do you call is this particular modality? I'm very sorry. I do not know why this sound problem is there from my end or your end. I don't have any idea about it. So then MRI also there is a, as you already know, you might have seen in the this thing also some YouTube video also that a person with a metallic implant, old implant, not new implants, old cardiac implants, either for defibrillator or for what, some artery thinning balloon surgeries, balloons, internal balloons, or then what, this pacemakers, previous old pacemakers, like let's say 15 years old, 10 years old. If it is within 5 years, there is no problem. They can this thing up to 1.5 Tesla of this thing, what do you call, MRI, this thing, MRI impact, there is no problem. But despite of it, this is very critical. Patient should have multiple different arrangements so that MRI can be done successfully. So, and then this ultrasound. In ultrasound, the contraindication is if it is excessive obese. What happens? No, fats are a different kind of tissue. fat tissue is not a normal tissue. Why? Because in fat the amount of water is less. So as you know that most of the imaging modalities, no, they are this thing on hydrogen atom. So fat is a hydrophobic thing. Hydrophobic means water hating thing. So if there is a large buildup of fat in the body, multiple imaging modalities will give you bad response. So it is limited by AR, bone, and excessive obesity will also give you a bad result in ultrasound. So each and everything we will try to incorporate in the same digital tool itself, this one. Now this is our long-term goal, and we will collaborate with some company so that we will add this thing, because we have to again subscribe to a new this thing library to put this particular button here. So we have purchased many licenses and many this thing in our lab in order to build these tools and to collaborate with this thing. So by saying so, I would like to conclude, and I'll be very much over this thing that if anyone like to collaborate with us for building a digital tool for their teaching learning process, for their research purpose or doing things, we are very much this thing open for collaborations. By saying so, I have come to this thing end of the this thing discussion. Right now we cannot share the links of the tools to you directly, because we are in talk with some third party for a kind of share profiting collaboration, and therefore our branding is only been seen. Once it has been finalized, we will give it to the third party, then the third party will be selling it to different colleges and schools. Can we open our session for discussion, madam?
Yes, sir. So, dear participants, if you have any questions, please post in the chat box.
Yes. Please post so that we can have a yeah, PPT can be shared later on. Yes, why not? But the links of these tools may not be this thing.
PPTs and videos we will share through WhatsApp group. If you have any questions, please write in the chat box.
Thank you.
Yes, sir, there are no questions. We'll conclude this one, sir.
Okay, madam.
Okay. Sir, on behalf of AICTE Atal Academy and SNIST, I extend our sincere thanks to Dr. Surajit Debnath for the highly engaging session on implementation of medical image denoising schemes using deep learning and machine learning. Sir, your clear explanation of denoising concepts and real-time examples enabled our participants to clearly understand how these techniques can significantly enhance medical image quality for accurate diagnosis. The practical insights you shared have greatly strengthened the participants' confidence in applying these techniques in teaching as well as in research. We truly appreciate your time and efforts, sir. Once again, thank you very much, sir, for your valuable contribution to this FDP. Thank you very much, sir.
Thank you.
Yes, dear participants, tomorrow session starts at 2 o'clock. We are going to have 3 sessions. As we know, Ashwini madam is going to take the first session, 2 to 3:30. It is continuation to the previous session, what she was spoken on CNN architectures, followed by generative adversarial networks by Mr. Shivaram K.R. And then that is during 3:30 to 5 p.m., followed by research trends and case studies in healthcare using deep learning by Dr. M. Purnachandra Rao. That is from 5 to 7:30 p.m. So, and then we're going to have valedictory and online test. So I request all the participants be join on time, and the test you have to give through Atal portal only, and you need to submit the feedback through the same Atal portal, then only certificates will be generated for you. And one more point is the test link will be active for specific time interval. During that time interval only you have to complete. And another note is the minimum of 80% attendance, and the test score must be minimum of 70% to get the certificate. We will share all the details once again in the tomorrow during the sessions, as well as in WhatsApp group. So I request all of you, please be active in WhatsApp group. We will post all the information through WhatsApp group. Thank you for your patience listening and bearing with us. Thank you very much. We will meet tomorrow at 2 p.m. Good night.